Hi everyone, welcome to lesson 1 for ratio and rates, stage 5.2. The outcome is this one, and our learning intention is to solve problems involving direct proportion and to explore the relationship between graphs and equations corresponding to simple rate problems. Today, you know you're making progress if you can convert between units for rates. And today we will look at kilometers per hour to meters per second. So that conversion. First of all, let's just make sure we can do the basics. So the first thing we do is the revision questions. So they go in our workbooks. Remember, pause the video, do the questions, and then check your work. Okay, so you've done the questions. 2 kilometers equals 2,000 meters. So we times by 1,000. For question 2, 3,000 meters equals 3 kilometers. So we're dividing by 1,000. 3 hours is 180 minutes, so we're timesing by 60. And 240 minutes, we divide by 60 to get 4 hours. Okay, so here are the examples. Just making sure everybody gets that 1 kilometer is 1,000 meters. 1 hour is 60 minutes. 1 minute is the same as 60 seconds. And 1 hour is this many seconds, 3,600, because we times these two numbers together. 60 times 60. So you'll see this soon get used in our calculations. 1 kilometer per hour equals 0.27 recurring meters per second. To get this number, the 0.27, we use 1,000 divided by 60 times 60. So if we convert 5 kilometers per hour, 5 kilometers is 5,000 meters. So we times by 1,000. If we go per hour, we divide by 60 times 60 to change it per second. So that's where these numbers come from. So 5 kilometers per hour is 1.4 meters per second. So our process is, if we have a variable, so if we have some number of kilometers, whatever that number is, we times by 1,000 over 60 times 60. So we're going to use this process a lot. While we're here, we'll talk about 800 meters. So if we want to convert that to kilometers, we divide by 1,000. So 800 meters is 0.8 kilometers. 100 minutes is 100 divided by 60 hours. 100 seconds, we divide by 60 to get minutes. So 1 meter per second is 3.6 kilometers per hour, 3.6 recurring. So 4 meters per second would be 1 times 3.6, which is this number here. So it's similar to this one, except for we multiply by 60 times 60 and divide by 1,000. So to go from seconds to hours, we times by 60 and 60. And for the meters, 4 meters is 4 divided by 1,000 kilometers. So 800 meters, we divided by 1,000. So dividing by 1,000 here is the same as dividing by 1,000 here. Same reason, we're converting meters to kilometers. So 4 meters per second is 14.4 kilometers per hour. Our process is this number. So if we have a certain amount of meters per second, we times it by this number to get kilometers per hour, which you'll do in the next questions. So here are the questions. Do the answers in your workbook. So pause and then play. Pause the video, do the questions and then play. 60 kilometers per hour. We times by 1,000 over 60 times 60. 60 kilometers times by 1,000 to get meters. Divide by 60 to get minutes. Divide by 60 to get seconds. So this is our process. We'll do the same thing with 100 kilometers per hour. Before I talk about that, if you put this into your calculator, okay, dividing works the same as using the fraction. Notice that divide by 60. When we do our fractions, we actually go 60 times 60. So back to 100 kilometers per hour. We times by this number, which is 27.7 meters per second. Again, you'll notice this is recurring. If you're not sure what recurring means, you can see here. The 6's repeat, and it rounds up to 7 at the end. Or we can just write it with a dot over the top. This is an exact value. This is an approximation because it's actually rounded. Okay, now for meters per second, our process is these get flipped around. So 10 times 60 over 1,000, which is 36 kilometers per hour. On your calculator, you could do it like this as well, or use the fraction bar. Okay, a problem here, Usain Bolt, hopefully everyone knows who he is, very fast runner, ran at a speed of 14.72 meters per second. How fast is this in kilometers per hour? So he was a Jamaican sprinter, ran very fast, 14.72 meters per second. Same process as above, times by this number. So he was running at 53 kilometers per hour. Okay, I want to connect this kind of situation to graphing. So for our examples, which go in your notebook, if we were to draw a graph of a car traveling at 100 kilometers per hour, we would draw a table of values first. So time and distance, 1 hour, 2 hour, 3 hours. The distance we times by 100 to get 100, 200, 300. Drawing the graph, it would look like this. We'd make sure we put arrows on, which GeoGebra doesn't do very well. Okay, so we've got distance in kilometers vertically, time horizontally, and this title could go over here as well. So a few things to note. The gradient, so the rise over run, I've got in my calculations 200 minus 100. So this part here, so I'm talking about the rise, so the rise from here, and the run is 2 take away 1, so the run is this bit. So we have rise over run. So it rises 100 and runs 1 hour. Remember, we need to use our scale. So 100 over 1 is 100 kilometers per hour. So for this context, the gradient of the line is the actual speed of the car. The equation of the line would be 100 times x. So if x was 3 times 100 is 300. This is a direct relationship. So as this increases, as time increases, so does distance. It's a direct relationship. We're timesing the horizontal part by 100 to get the vertical part. It's a direct relationship. As time increases, the distance traveled increases. So I would like you to draw a graph for another car traveling at 80 kilometers per hour. That's what you can do for practice. And try to state these things as well. So what does the gradient mean? What is the equation of the line? And is it a direct relationship? Okay, good luck.